Today we're going to look first at how to extend what we've been doing so far with binary classifiers, extend that to any number of classes, so multi-class classification. And then we're going to look at some more theoretical concepts of bias and variance, I hope. Está mal encaixado. So we're going to look at bias, which is an average deviation of the model predictions from the target value, and variance, which is a measure of scattering of the model. And we're going to see how these relate to the problem of underfitting and overfitting. And then in the second lecture we'll see how we can use this to try to improve classification by aggregating results from several classifiers. But now in the first part we're going to look at bias and variance, computing, and their relation, the trade-off between the two, and the relation to underfitting and overfitting. But I'll start with this part. So far we've been seeing only binary classifications. All the examples we'll be looking at had two classes. But some classifiers we can easily extend to any number of classes. For example, the k nearest neighbors classifier outputs the majority class from those k nearest neighbors of any example we want to classify. So this can work trivially for any number of classes. You just have examples of the different classes in your training set, and then the classifier will get a majority vote from all that neighborhood and output whatever class that is. The naive-based classifier, we classify an example by looking at the class which has the maximum prior probability of belonging to that class, multiplied by all the conditional probabilities of the features in those classes, of the feature values. Or if you do it in logarithms, you add the logarithms. This can work for two classes, but it can work for three, four, for any number. It's exactly the same thing. You just do it for all the classes and choose the one with the highest probability. So these are examples of classifiers where it's trivial to solve a problem for any number of classes. However, there are other classifiers where this is not so easy. So we're going to start with this classical example, the iris dataset. This is a dataset on measurement on flowers of this kind. And there are three genera of flowers here, Cercosa, versicolor, and virginica. And they have different sizes on the petals and sepals. And so we have four attributes: sepal length, sepal width, petal length, and petal width. I'm going to project this only to two attributes to illustrate, but basically we have these different types of flowers, and we can represent them. In this case, this is the horizontal axis here is the sepal length, and the vertical axis is the sepal width. And just with these two features, we already have some fairly good separation between the three classes. So this is an example of a classification problem with three classes. If we use k nearest neighbors, for example, it would be trivial because we just classify each point according to the majority class of the nearest, in this case, 15 points in our training set. So it doesn't matter how many classes we have, we just count how many of each we have in those 15 points and choose the majority vote. But if we have some classifier that uses, for example, linear discriminant, like we saw with logistic regression, with a multi-layer perceptron, or support vector machine, or something like that, where we are dividing the set of examples into subsets, then we need to find some way of solving this problem, of extending this to a larger number of classes. So we're going to consider three generic solutions to understand better why the last one is the best. But one idea would be we train one classifier to classify one class and distinguish that class from all the rest. And then we do the same for other classes, and we only need to do this for k minus 1 class. So if we have two classes, we only need one classifier. If we have three classes, we only need two, because whatever remains is the remaining class, and so forth. We could also do all pairs of classes. So we have a binary classifier. We need to extend this to any number of classes. So we create classifiers for all the binary decisions between one class and the other. Or we could do one classifier for each class and then take the maximum of the decision function. So we're going to see the advantages and disadvantages of these options. Let's start with the first one. We're going to create for k classes k-1 classifier. So if we had 2 classes, we would create 1 classifier. If we have 3 classes, we create 2 classifiers. And what we do is train each classifier to identify its corresponding class and distinguish it from all the rest. And then we look at the final results. For example, we create 1 classifier to identify setosa. These are the blue ones here. We create 1 classifier to distinguish versicolor, which is the green one, from all the rest. And now whatever is left outside the 2 would be Virginica, which is the third class. So we could then combine these 2 classifiers. This would be setosa, this would be versicolor, and this here would be Virginica. So in this way, if we have 3 classes, we only need 2 classifiers to classify an example. The problem is what happens here, because here one of the classifiers is saying it's versicolor, the other is saying it's setosa, and we don't know how to classify this part. So if we do it this way, if we have 1 classifier for 2 classes, we don't have this problem, because there is no ambiguous zone. But if we have 2 classifiers for 3 classes, we can have an overlap of these 2, and then we don't know which class to assign to that point. So one other possible approach would be to train all the pairs. So we train 1 classifier to distinguish setosa and versicolor. So we are just looking at the blue and the green, we are ignoring the red, and we are creating a classifier to distinguish these 2. Then we look at setosa and Virginica, so in this case it's blue and red, and then we try to distinguish between green and red. So we have 3 classes. We do create classifiers for all the combinations of 2 classes, and now we have 3 classifiers. Again, we have regions where we can decide which one they belong to, because we can split between the 2 classes and figure out which of the classes is there. But there are regions where the classifiers disagree. So one of them is saying it's one class, the other is saying it's the other, and we cannot assign a class to those points. So these 2 approaches, either creating k-1 classifiers and then leaving out the remaining class on whatever is left, or creating binary classifiers for all the pairs of classes, gives us this problem of there being points where the classifiers disagree and we cannot solve how to assign a class there. So this is why what we usually do is this k1 versus the rest classifiers. So if we have 3 classes, we create 3 classifiers, each one trained to distinguish 1 class from all the rest. So this one is trained to distinguish setosa from the rest, this one is trained to distinguish versicolor from the rest, and this one Virginica from the rest. Of course, when we put them all together, there will be overlapping regions. But now we don't look just at the classification, we look at the decision function. So this decision function is that function where we assign some threshold when we have a binary classifier to distinguish between one class and the other. For example, with logistic regression, we have a regression to a probability estimate, and we usually put the threshold at 0.5 to distinguish between one class and the other. If we have some, for example, support vector machine, we have a measure of the distance to the discriminant, and we can use that as a decision function. So what we do at the end is we aggregate the 3 classifiers, and we assign to each point the class corresponding to the one that gives us the highest decision function. So since these are continuous values, even if they have overlap, we can decide because we pick the one with the largest decision function. So this would be the result of using these 3 logistic regressions trained for binary classification, in this case, these linear classifiers, and then aggregating everything and using the decision function to decide which class they belong to. So the advantages here of using this one versus rest, this is the standard way of extending binary classifiers to n classes, is that since we classify using the maximum of the decision function, we generally don't have problems with ambiguity because these are continuous values and there are seldom any ties. So this helps us solve the problem of ambiguity when we combine binary classifiers. There are, however, some problems here. Since we have to train the classifiers to distinguish one class from everything else, we will tend to be dealing with very unbalanced problems. So suppose that we have 10 classes and the examples are uniformly distributed among the 10 classes. This means that each class covers only 10% of the examples. So when we train one classifier to distinguish that class from the rest, we have the class 1 is 10%, the positive examples are 10%, and the negative examples are 90%. So some classifiers may not perform well when the examples are very unbalanced. Another problem is that in order to aggregate the results in this way, the predictions, we are using the decision function, but the actual values of the decision function depend on many factors. For example, we know that the size of the vector in logistic regression or in support vector machines will determine how steeply the decision function increases away from the discriminant. And so if we train two classifiers and those vectors have a different length between them, then it may not be reasonable to compare the values of the decision function for any point, and we can get some errors, some biases in that way. So these are the problems with one versus rest classification, but in any case, at least we get something. We can take a binary classifier, combine it like this, and get a result and classify for any number of classes. Now, some classifiers we can extend them in different ways. For example, with logistic regression, we use this target function where we raise the prediction to the class. So for those that were class 1, it was raised to 1, and then we had part of the expression 1 minus the class, and this way we were switching on and off the examples depending on which class they belong to. We can extend that to any number of classes by using this function for each example, which basically, for example, n, this function t of example n for each class k is 1 for the class the example belongs to and 0 for all the other classes. So when we are computing this expression over all examples and all classes, each example will only count for the class it belongs to. And this way we extend that target function, that sigmoid function, to an arbitrary number of classes instead of just 2. And then we can use this for the logistic regression, extending the cross-entropy error function that we wanted to minimize. So this in scikit-learn is called a multinomial. You have this string here. This is a multinomial logistic regression, and you can use that way of classifying for more than 2 classes using the multinomial argument there, in the value in this multiclass argument. Alternatively, you can use the one versus rest. So in this case, this trains only one logistic regression, but with this loss function, so extending for the whatever number of classes you have. This option, when you use one versus rest, trains k logistic regressions for distinguishing each class from all the others, so as many classifiers as the number of classes you have, and then uses the maximum of the decision function to classify either of them. For a multi-layer perceptron, usually what is done when we have to classify more than 2 classes is to use one output neuron for each class. So if you have only 2 classes, you can have an output neuron with a sigmoid function and interpret that as the probability of belonging to the class. Since the sigmoid function goes from 0 to 1, we can interpret the result as a probability and assign to one class if the output is greater than 0.5 or the other if it's lower. If we have more than 2 classes, we can have an output with the same number of neurons as the classes, and then aggregate everything with this softmax function. So this function receives k inputs and outputs k output values, so outputs a vector of the same size, but it computes each of the value with these exponentials divided by the sum of the exponential for everything, which means that the sum of these, yes? Because now you have a vector with values that go between 0 and 1, so all of these are between 0 and 1, and the sum of them is 1. So you can interpret this as the probability distribution of belonging to any class. So suppose you have 10 classes, you have 10 values, and they can be interpreted as the probability of belonging to class 1, to class 2, and so forth. No, the input in the network would be any size. Then you have several layers, multi-layer perceptron, and then at the end you have 10 neurons. If you have 10 classes, you have the same number of neurons as the classes, but instead of each neuron having its own output function, its own activation function, the activation function is a function of all of these 10 and outputs a vector of 10 values, or whatever number of classes you have, that has these properties. So each value is between 0 and 1, and the sum is 1. This means we can interpret it as a distribution of probabilities of belonging to any class. If they are all the same, for example, it means the network is undecided. If one of them is high and the other low, the network is classified into that class. Okay? So this is a standard way of using having a multi-layer perceptron classify in a larger number of classes. So for the general solution of 1 versus rest, this is when you have binary classifiers and just want to aggregate them. You can use the 1 versus rest classifier in scikit-learn. This is an aggregate classifier that receives this initialized classifier. For example, in this case, I'm using the support vector classifier class. I give these meta parameters, and so the 1 versus rest classifier will create copies of that classifier, train each of the copies for classifying one class and distinguish from the rest, and then when we call predict here, it will predict according to the decision function of the different classifiers. So this is a way that is already implemented that makes it easy to combine binary classifiers for n class problems, and this would be the example of this result. So if we use 3 support vector machines with the Gaussian kernel, gamma 0.7 and C of 10, in this problem with the iris flowers, then we get this result of the 1 versus rest classifier. These are the regions where each of the classes has the largest decision function value. Okay, so this is for solving problems extending from 2 classes to n classes. Depending on the classifier you have, you may already have, the classifier may be able to do that with some changes or even with no change at all. Or if you have binary classifiers, you can aggregate them in this way and extend it to n classes. So now let's go to some theoretical concepts that will be important for the second hour. And the first one is bias. We already used this term in inductive bias, which is what we need to presume or we impose when we select a class of hypotheses. The meaning of bias in this sense here is different, is bias in the statistical sense, which is basically the difference between the average of some prediction and the target value. So if you are shooting at the target and are always missing by shooting higher than the target, that average difference would be the bias. So let's imagine that we have a model that cannot properly fit the data. The data curve is more or less like this. The model is not flexible enough to fit the data. And so even if we train different hypotheses, we train the model on different data sets and obtain different hypotheses. For example, all these different colors would be different samples from the data. For example, we could repeat our measurements or obtain new data or something like that. We train our model again and again. We get slightly different hypotheses, but they always overestimate the value here. So you see the average there, the average prediction there is quite distant from the target value at that point. So this measure, the difference between the target value and the average of our predictions is the bias. You see that our model is biased because it's always overestimating the data in that point. Of course, in other places, for example here, it tends to underestimate the data. It may not be over all the data set, it may not have exactly the same bias. So this is the definition of bias. It's the quadratic difference between the target value and the average of the predictions. So this average of the predictions in theory could be over an infinite number of data sets, an infinite number of samples from the universe of possible points. This would be for each point. So this is the bias for point n, is the quadratic difference between the average predictions for point n and the actual target value for point n. The average of this is the bias of the model. So we sum the bias for all the points, we divide by the number of points, and this is the bias for the model. Note that bias is something that is a property of the model and not of any specific hypothesis, because of that average there. Okay? Sometimes you'll see bias written as bias squared with that too. This is just a notation that refers to that square there. It doesn't mean that we're actually computing bias squared, it's just that it's a quadratic error. Okay? Another important measure is variance. Nobody seems to be in panic, so I presume it's a false alarm. So variance, imagine that your model is overfitting. This would be where variance is higher, and the model produces hypotheses that are too adjusted to the data, so fit the data too much. Let's hope it's not a real alarm. So if this happens, then what we have is for each sample we get, the hypothesis can be very different from the previous hypothesis. It can vary widely from one sample to the other. And so when we look at the predictions for a given point, there is a wide dispersion of these predictions, depending on which data points were used to train the model in that instance. So this is the definition of the variance for point n, is the average of the quadratic distance between the average prediction and each of the predictions. Note that variance is not about the relation to a target value, it's just about the dispersion of the predictions. So we are measuring the distance between the average prediction and each individual prediction. The average for that, so the average of these quadratic differences that we have here to the average point will be the variance for one point. The variance for the model, again, it's not an attribute of any specific hypothesis, it's a statistical property of the model, will be the average of the variances of all the points. So basically, we have to sum all the predictions for each one point, and the difference between that prediction and the mean prediction for that point. So this would be this sum here, and then we have to do this for all the points and divide by the product of the predictions and the points to get the overall mean for that. So basically, bias will give us a measure, the quadratic difference between the average prediction of the point and the target value. This is how our point is biased towards higher or lower values or something like that. Variance gives us a measure of how spread out the predictions are, regardless of where the target is, but the variance here on the prediction. So remember that bias and variance are statistic properties of the model, because they are what happens on average when we train the model over different training sets, and then we evaluate its predictions. So let's see how we can measure this and how we can use this, at least conceptually. Let's suppose that we have a quadratic error loss function. So this is typically what we use in regression, which is the error of our model will be the expected value, the average over all possible points, of the quadratic, of the square of the distance between the target values and the prediction. So y is the prediction, t is the target value, and if we average over all possibilities this error, this is the error of our model. But we can decompose this into three terms. We can look at the quadratic difference between the average prediction for a point and the average target value we have for that point. Add the average or the expected value of the difference between each prediction for that point and the mean prediction for that point. So this is bias, the difference between the target value and the mean of the prediction. I have here an expected value for the target because we can also assume that there is some error in the data. This is the final term, noise. The second term here is variance. So basically we are decomposing the error into these three terms. One is how our model is bent, so to speak, and biased towards some particular type of error. This is the first term. The other is due to the spread of the predictions of our model. And finally, the third term is not about our model, it's about the data, because there may be some error between the actual value that we wanted to predict and the value that we are using in the model, because we may have error in measurements and things like that. In general, we're going to ignore this third error because we cannot do anything about it. This would be some problem, some noise in our data, but we cannot help that, so let's pretend that is zero and decompose the error in bias and variance. So one thing that is useful here is to think about the error of our model as the sum of the contribution of the bias of our model, which is related to underfitting, is the ability of a model to properly adjust the data, which makes it have some tendential error. And then also the contribution of variance, which is related to overfitting, is what increases in overfitting because it's the ability of our model to adjust too much to the training data and then make wildly different predictions from one case to the other. So if we can measure this, we can get an insight into what's happening with our model. The thing is that we need to average over different sets, and usually we only have one data set. We do not have the luxury of obtaining more data as we need. So we're going to need a resampling method. This is a mathematical trick to pretend that we have more data than we actually have. So we're going to do bootstrapping. You have a training set with a given number of examples. And now imagine that you sample examples from that set with replacement. So sampling with replacement is like you have a bag, you take one at random and you put it back in the bag. So you keep taking and putting back and noting the values that you get. This means that you can get the same example more than one time. You can repeat some examples. If you obtain a sample that has the same size as the original set, some of the examples will be repeated, so some of the examples will be missing because the size is the same. On average, about 1/3 of the examples will be repeated, so on average, each sample that you obtain with bootstrapping will have 2/3 of the data randomly chosen and the rest filled with repetition. This means that if you create these replicas, each one will have a different set of points from your original training set. However, the distribution of the values that you get, the distribution of the examples, will be the same as your training set because you are sampling from your training set. So this allows us to simulate what would be if we could obtain a new training set from the same universe of points where we got the first one. Okay? So this is what we're going to do to get the replicas of our training sets to train different hypotheses of our model. We also want to estimate the errors, and obviously we cannot train our data with a set of points and then estimate the errors on the same points because that will not give us a good estimate of the error. So we're going to have also a test set for estimating the points. This can be a validation set if then we use those results to choose the best model. But remember that the difference between a test set and a validation set is basically what use you give to that set later on, because each of the error estimates outside the training set by its own is unbiased. When you take a group of them and then choose the lowest one, that's when the process makes the results biased. So we are going to use the test set to estimate the error, a set of points that is separate from that set we use to create the replicas. And then if we use those test sets to choose the best model, those are actually valid. It's actually a validation set because now the estimate is no longer unbiased. So this is how we could implement bootstrapping. We have a matrix of data. This could be the training set, for example. The number of samples we want to extract with bootstrapping. And so we look for each, iterate the same number that we have in samples, and we create a random array of integers ranging from 0 to the size of our data. Actually, it's the size -1. It will never be exactly that. So that way, we are creating a random set of indexes to this data matrix here. And this is the number of points that we want. So since these are randomly created, there may be repetitions there. So some of the values will be repeated. And since it's the same number as the size of the matrix, some values will not appear because of the repetitions. So each time we do this, we pick at random a subset of our original data and fill everything else with repetitions at random. So each of these selections will have a different set of points. So now we're going to stack all these in a matrix. So we're going to, we created this matrix. Note that this is a three-dimensional matrix. We have on the first axis the number of samples that we want, and then the shape of the original matrix. So these are like layers of the original matrix, but we have random copies of the values drawn with reposition. So each of these slices, each of these matrices will be slightly different. Okay? So then we return this three-dimensional matrix with all the samples of all the matrices. And now let's do this to decompose bias and variance with polynomial regression. We can start by getting the samples from there. So we have here the training sets are just this matrix, this three-dimensional matrix with all the samples. And we have a test set to measure the error. So for each of the samples we obtained by bootstrapping, we're going to fit one curve, one polynomial of some degree that we get from in the argument, and then we're going to compute the predictions on the test set. So for each of these samples obtained by bootstrapping, we get a different hypothesis, we get a different set of predictions. Now, from all the predictions, we can compute the mean prediction for each point. So these predictions will be a matrix, which each row corresponding to one different hypothesis of the model. And now, if we compute the mean along the rows, we get the average prediction for each point in our test set. And now we can compute the bias for each point simply by the difference between the mean prediction and the actual target value squared, and then the bias for the model by averaging over the points. The same thing for variance. We can use the mean prediction and the quadratic difference between each prediction and the mean prediction, and then we average that, and this gives us the bias for it, the variance, for each point. When we average the variance over all the points, we get the variance for the model. And now we can plot these, and this is what we see. So this is the red line here is the error, which is the sum of the two contributions, the bias and variance. And you can see when we have models, so in this case the curves have a lower degree, we have a large bias and a smaller variance. As we increase the degree of the polynomial, the bias starts to decrease because now the polynomial can adjust better to the data, but eventually variance starts to increase a lot because now the polynomial adjusts too much. So you see the same curve as we saw with, for example, cross-validation or validation training and validation to select the best model. This red line has the same kind of curve we saw previously, but now we are seeing the contribution of these two factors. Bias is the inability of the model to adjust, so it tends to tendentially make the same kind of mistake. Variance is when the model is adjusting too much, so variance increases because now the dispersal of the predictions is high. So this is basically the same thing we measure, but now we are decomposing into bias and variance. We can do the same thing, we can use this for selecting the best model, exactly how we did for cross-validation. So basically the best one will be the lowest sum of the bias and variance errors. We can do this also with classifiers. In this case, it's, the computations are a bit more complex, but the idea is the same. So bias, let's consider this loss function L, which is 1 if the two arguments are different, 0 if they are not. So basically, it's a measure of the error. It's 1 if we are not hitting the right value, it's 0 if we are hitting the right value. So the bias for point I will be the loss function between the majority classification over all the hypotheses we obtained in the model. So this is typically the mode of the classification. Think about classifications as being between 0 and 1. We do it, for example, for 100 replicas of our training set, and if 80% of them give 1, then this is the majority vote. It's the mode of all those classifiers. So this would be the majority vote for our classifier, and this is the target value here. And the bias for each point is 1 if there is a difference between the majority vote and the target value, or 0 if they are the same. The variance would be the average of the loss we get when we compare each prediction to the majority vote. So it's the same idea. We are looking at the spread, and the variance will be higher when the majority vote is not a big majority. For example, if it's 51%, then there is still 49% of the cases where the prediction differs from the majority vote, so that will give us a higher variance. If the predictions are all the same, then variance is 0 because there is no dispersal test. Now, when we are considering how these two contribute to the error, things get a bit more complicated than in the other case. Because now, if we have a point that has a bias of 0, it means that the majority vote is correct. In that case, variance means that the error is increasing, because variance means, for example, the difference between having a majority vote 51% of the time, so 51% of the times is correct and 49% is not, or 99% of the time. This would mean that 99% of the time is correct. In that case, variance, a higher variance means a larger error, because the point is correctly classified in the majority of the cases. But if bias is 1, this means that the point is not correctly classified in the majority of the cases. Higher variance means lower error, because suppose that 51% of the time it's being misclassified, that's not as bad as 99% of the time being misclassified. But 99% of the time would mean a lower variance. So variance decreases the error when the point has a bias of 1, and increases the error for points that have a bias of 0. So actually, when we do the decomposition, what we are looking at is this difference between the variance on unbiased points and the variance in biased points. So if let's see an example with k nearest neighbors. We want to optimize the number of neighbors, and we're going to decompose into bias and variance. So again, we obtain a set of samples from bootstrapping. So we have a set of training sets that mimic what would happen if we could resample from the universe and get new data. We cannot do that from the universe, but we do it from the original training set by bootstrapping. And now we're going to train a k-nearest neighbor classifier with each of these each of these samples, fit it, and then we're going to predict on the test set. The test set is a different set of points, because we cannot estimate the errors properly inside the training set. And now we're going to find the main prediction. So in this case, since the classification is 0 or 1, we can average the predictions for each point and then round to 0 or 1. So if the average is above 0.5, it rounds to 1. If it's below, it rounds to 0. Note that if you have classes of -1 and 1, then you have to do the calculations differently. So this is not something fixed for any case. It's just that in this case, I'm considering classes of 0 and 1. So this gives us the bias per point. We are computing the difference between the target class, which can be 0 and 1, and the main prediction. We get the absolute value, so the bias is 0 if the main prediction corresponds to the class, and it's 1 if the main prediction is not the same as the target class. And then we compute the variance too. In this case, we are averaging the difference between the main prediction and each prediction. So all these differences we average, and then we are going to decompose the variance into two cases. One where for the points that have no bias, and the other for the points that have a bias, because these variances contribute differently to the error. If the point does not have bias, the variance adds to the error. If the point has bias, then the variance subtracts from the error, because at least some of the time we are getting it right. And then we return bias and the net variance, the unbiased variance minus the biased variance. So this would be the two contributions to the error. Now the plot is a bit different, so we don't see variance increasing so much here. Also, an important thing, this plot is reversed from what you usually see, because note that with k-nearest neighbors, the lower the neighborhood you're looking at, the higher the sensibility of the classifier to local events and to details in the data set. So actually you get overfitting on this side and underfitting on that side, because if you increase the neighborhood, you stabilize things, but you make it harder to adjust to details in the data set. Okay? So remember also, I'm using this example because sometimes you may get fixed in some pattern and be expecting underfitting to be on one side, overfitting on another, but it depends on how you plot the graphs and what are the parameters and what the parameters mean for the classifier. So remember always to think about and to those things and understand what are there. Okay? So here we get the different contributions of the variance to the error. Note that we can get variance actually reducing the overall error, because we have variance on points that are misclassified. Okay? But again, we can see the total error, and we can use this to select the model. So in this case, we're going to select a model with 5 neighbors, and we have this result. So in general, what we can see is that there is a trade-off between bias and variance, because bias increases the more the model has difficulty in adjusting to the data, and it has some tendency to do some kind of biased error. Variance increases when the model adjusts too much to the data. So when we try to adjust some parameter to decrease bias, we eventually end up increasing variance and vice versa. And this is called the bias-variance trade-off. Decomposition into bias and variance is useful to understand what is happening in the model, but in practice we generally don't do this. This takes a lot more work than just doing cross-validation, and we have to sample a lot and so on. So this is not a practical tool, but it's important to understand where the error comes from. There are these two different sources of error. So to sum up this first part, we saw how to extend binary classifiers to n classes. That was just a parenthesis. It's an easy thing to do. And then we saw these concepts of bias and variance. So bias is this average error the model commits because it cannot adjust the data adequately. And variance is the dispersal on the predictions because the model is adjusting too much to the data and can have big changes, big instability depending on what the exact points are. So these are related to underfitting and overfitting because bias increases when you are underfitting and variance increases when you are overfitting. And it's also important to understand this composition when we see how to group models together to try to reduce these problems, which you're going to see after the break. So here are some book chapters that you can read. Also optionally, you have here the paper I based on for this part, this discussion on bias and variance decomposition for classifiers. Usually the simplest examples are with the quadratic loss error. With classification is a bit more complex, but if you want to look at the details, you have them there.